In this video, I'm going to show you how I approach root finding if I am giving a completely new function. And so I want to find all of the roots to, I don't know, let's say 5 or 6 digits of precision. And I don't know anything about the function. So right now, there is a function in memory called weird func. Weird func. And if I give it a number, it gives me something else. So by root finding, what parameters, what values do I give it so that it would return a 0? How on earth do I do this? Well, I like to do everything through a script file. So let me start a new script file. And let's name this find all roots.m. And I'm going to hit return a whole bunch of times because I just don't like the way MATLAB behaves when I'm typing on the very last line. So I will copy that, save as, paste what I just typed, and there we are. Now I can run it, and at the same time, it saves the script file and runs it. And you can see where MATLAB has actually typed in the name for us and have run it. The first thing I always do in MATLAB is initialize. So initialize MATLAB. I will close any open figure windows. I will clear any text from the command window to the right. And the most important one is I will clear memory. Okay, so what do we do? Well, we need to explore this function to at least crudely determine where it might have roots. So let's create a section header here. And we'll just call this explore function. Okay, that makes a nice visual separator for this section of code. All right, so we're going to make a first, or just call it plot function. So how many points should we use? Well, if this is a very slow function to calculate, I might want to start with a low number like 10 or 20. If it's fast, maybe I type in 100 or 1,000. So I'll type in 50 for a place to start. I need to calculate this function over some range of x. What should I do? Well, linspace, let me go from minus 1,000 to positive 1,000 because I have no idea where this is going to have roots. But we're going to do 50 points in that range. So now we'll calculate the function, and maybe we'll say y equals weird func of x. And then we'll plot the function. Plot x, y. Well, let's just run this and see what happens. Now, this is very typical of what we would get the first time we look at a function. And it looks like, well, maybe it only has one root. Maybe it's a quadruple root. And in fact, I'm completely wrong if I'm thinking that way. I might be thinking that way because I see it kind of touch 0 and go back up, and it's sort of this broad. But look at the axes here. Look at the magnitude of that, 10 to the 22nd. And then I can go in, I can try to zoom in, right? Let me zoom in the best I can. And I'm basically seeing the same thing. I'm seeing 10 to the 22nd. So zooming in is not giving me new information. But when I see I have this huge axis, huge magnitude here, and I see these numbers go off to infinity, I am pretty confident that it's not going to do anything interesting or above or below these bounds. So somehow I have bounded my interesting stuff to within the hundreds. But this is not providing me any new information. And I could keep zooming in, and it's basically just looking the same. So this is not doing me any good. But if all of the 0 crossings are crossing at 0, why do I even let my y-axis limits go up that high? Let's limit them. And I don't know, maybe minus 100 to 100. And let's run that and plot that. Now we're not seeing anything, and that's probably because we don't have enough points. And we also know that it's not going all the way out to 1,000, so maybe we'll go from minus 200 to positive 200. It seems to be running reasonably quick, so maybe I'll put in 100 discrete samples. Let's see where we are now. Oh, okay, so it looks like maybe something's happening more between negative 10 and positive 10. And it told me that because I just automatically set my y-axis limits, and it knew to chop the x-axis limits. So MATLAB's doing some thinking for us. But we can also zoom out, and we just keep seeing basically the same thing. So whatever's happening seems to be maybe between -10 and +15. Let's give that a try. -10, +15. We'll give that a plot. Okay. And now I see some ripples that are, wiggling around 0, but these all seem to maybe be below 20 and +20. Maybe that's the next thing I try, from negative to +20. And so the point here is I just keep playing with the x and y axes until I converge to something like this. And I'm pretty close now, and I can maybe even start making some conclusions about where these roots are. Well, one thing that might help, I would like to have a horizontal line right at 0. So why don't I just go ahead and add that? So I'm going to add a line. And in this first little array, it's the two x positions. Let's think of it like the start and the stop x position. Well, the very first one, I have this, lin space. So what I could do maybe is go from the first value of x up to the last value of x. And then for my two y values, well, I want to have this line right at y equals 0. We'll just stick there. We won't dress up the graphics too much because we're just crudely playing around. And already we see that there's probably 4 roots in this function. We have the function probably touches 0 here, probably crosses, well, definitely crosses 0 there, definitely crosses 0 here, and probably touches 0 there. And the way that it explodes to the left and to the right, even when I zoom out, I don't see anything else, tells me that there's probably nothing interesting outside of that. So there we are. Let me go ahead and just add now 200 points because this calculates pretty quickly, just for a smoother line. And we can figure out what order of the roots we have. And I'm looking at this first one here, and I see it touch 0 and go away. So I know already it's an even multiple root. If it was an odd, it would cross. So I'm looking at this root and this root. Those are odd roots because the function crosses, but here it does not cross. We have an even number of roots, and also over here we have an even number of roots. This one is very broad. That's probably a quadruple root. This one's quite narrow. That's probably a double root. Here we have a crossing, and the slope is roughly linear going across the line, so that's probably a single root. And here we have a crossing, but the slope flattens out. That is a triple root. So we have a quadruple root, a single root, a triple root, and then a double root. And we already have some rough numbers here of where they cross 0, and we can use these rough numbers to sort of seed our algorithm. So what algorithm can we use? Can we use the bisection method? Well, I think the bisection method would work for the second and the third roots, but it won't work for the first and the fourth because there's no 0 crossing. Now, of course, I could take the approach of calculating this auxiliary function, but let's not get into that here. Well, I think the one method that could probably work for all of these is the secant method. So let's go ahead and let's write a secant method, and then we can zoom in on the roots. So I'm going to create a section heading here and call this secant method. And so we will make a function called secant, which will implement the secant method, and then I can just call that to do all of my root finding for me. Well, I know a little bit about the secant method, and I know there's 2 values of x that we have, and I'm constantly updating the second value. So the second value really in the end becomes my root. So I'm going to output x2 instead of something like an xr, just because I know x2 will be my root. And I may also be interested in how many iterations it took. So I'll count those and also provide that as an output argument. All right, we'll call this the secant method. And now we need our input arguments. Well, we need the function that we're doing root finding on, so we'll be handing it a handle to a function. I forgot to say equals secant. We need 2 guesses at x, right, because we have to calculate a slope between them and then estimate our next line. And we also need some kind of tolerance to control the accuracy of this. So that's pretty much it for our function. I'll type in end. Now we need to implement the secant function here. And following the block diagram in the notes, the very first step is to evaluate the function at x1. So we'll call that f1 equals func at x1. At this point, we have our main loop. So I like to do this when I have a main loop, a little triple comment there. All right, and we will be using a while loop, while something, and then end. Well, what's that something? Well, we're going to have a change from iteration to iteration. That's dx, and that could be positive or negative. So what I want to do is just look at the absolute value of that, and I want to keep iterating as long as that is greater than or equal to my tolerance. Or I could just do greater than tolerance. It probably doesn't make much difference. I'll say greater than or equal to because that's the mood I'm in. Okay. Well, the first step inside the loop, following the block diagram in the notes, is to evaluate the function at x2. So let's do that. f2 equals func at x2. Now we want to calculate how much we need to change x. So what's happening behind the scenes here is we have 2 points. We can connect those with a line. That gives us a line that we can figure out where that crosses the y-axis, and that's our guess at the next root. And when all is said and done, we calculated a little formula to figure out how far we need to move x2 in order to get to that next root. So calculate, I spelled calculate wrong, calculate dx. So dx, and this is just following from the notes, f2 times x2 minus x1 divided by f2 minus f1. Next step is adjust the points. And what we're doing is we're copying the information from the second point over to the first point. So what was our second point from the previous iteration now becomes our first point for the next iteration. But we don't want to reevaluate the function. We've already calculated there. We just copy the information over. So x1 equals x2, f1 equals f2. Now that we've copied the information over, we can calculate our new x2. Oops, x2. So x2 is x2 minus the dx. And we don't have to evaluate the function at x2 because that's going to happen next time we repeat the loop. We're really done the secant method. Hopefully this works. One last thing, we said we were going to count the iterations. Count iterations. So we'll say iter equals iter plus 1, and then we'll track the number of iterations. That's it. That's the secant method. That's simple enough that I hope we did not make any mistakes, but we'll find out very shortly. So now we scroll up and let's identify our roots. So that'll be the next section of code. So this will be identify roots. So find root 1. Well, what do we do now? Well, let's go back to our plot. And we need 2 values of x pretty close to the root that we can seed our function with. So one thing that I might do is zoom in right here and get my values of x from this. And I think the crossing's right around, minus 5.4. So I might choose minus 5.4 and minus 5.3. Right? I'll pick these 2 points and let that fit into a line and zoom in. So if everything works, we should get our root from this function secant. It should tell us the number of iterations. So we call secant. First input argument, we have to give it the function, and we want to give it a handle to our weird function. We now give it these 2 values of x. I think we said minus 5.4 and minus 5.3. They're just 2 values of x close to the root, as close as we could roughly get. And a tolerance, 1e minus 7. So this means the change from iteration to iteration will be less than 10 to the minus 7. That tells us our number will be accurate probably down to the 6th digit, not the 7th. but definitely the fifth digit. So I like the tolerance to be at least an order of magnitude smaller than the last digit that we want. So if we want, let's say, 6 digits of precision, so that'll be a number like -5 point, and then 5 more decimals, well, that would be -5 to be exactly at that fifth decimal, but this would make that fifth decimal probably not very accurate. I want to come down at least an order of magnitude smaller. I'm coming down 2 orders of magnitude smaller, and I can be pretty much guaranteed that that fifth decimal, so I have 6 digits of precision, will be accurate. Well, we don't know if our secant function works. Let's run it and see if we get an error or if it freezes or who knows what'll happen. So let's run it. If everything works, it should return very quickly. We got an error. All right, what is it? Unrecognized function or variable dx. And what is going on? Oh, I see what happened. So we have our while loop. It's checking what's happening with dx, but we have not created our dx yet. So dx, let's set it to infinity. So that's huge. It'll always enter the main loop. Oh, you know, we need to initialize our iterations too. Start those at 0. Okay, now let's run it. Whoa, it returned pretty quick. So I have a feeling it worked. And our root is somewhere, I don't know, what would you call that? -5.5 or something like that. Well, we haven't looked at what our root is. Hopefully it came out in XR. Let's type in XR. -5.4321. Well, hey, I think that's correct. It converged. It was quick. Let's display our results. Display. And we would like to display the root and also the number of iterations at the same time. So let's say XR equals, and now I'm going to use num to string. And I want to display my root, but I also want to control the digits. And so if we want to display 6 digits of precision, well, there's a -5, so we only need 5 decimals. So we would do something like %7.5f, 5 decimals, 7 characters total, 5 decimals. And if we run that, that should give us our root. So we see that. And we want to also know the number of iterations. So we'll just add on to that text string, and we'll say in num to string iter. That's just an integer, so we don't need to format it at all. Iterations. And now if we run it, so 58 iterations. That tells me that our function's probably rather nonlinear because that's a lot of iterations, and the secant method likely was not the best to use here, or I just needed to make better guesses or something else. But you know what? This is a pretty weird func is pretty fast, and that's not bothering us, so we won't bother to change that. Let's find the second root. So we have to go back to our plot and just crudely figure out some numbers of 2 numbers to give our algorithm. And you know, what about 1.2 and a 1.4? So here and here. Yes, we could maybe 1.2 and 1.3. Yeah, we'll do that. So we'll just copy and paste that, but we're finding root 2. And what do we say? 1.2 and 1.3. And we want the same tolerance because we want the same accuracy. Let's go ahead and run that and see if it doesn't freeze. And we got another root, 1.23457. And that happened in 4 iterations. That's really good. Well, notice how linear that was. So no wonder it works really, really well. It works best for linear functions. All right, let's keep going. Find root 3. We need to get our plot back. This is our third root. Let's go ahead and zoom in there and pick some numbers. What about 7.7 and 7.8? Let's try that. So we'll do 7.7 and 7.8, keep the same tolerance. And there's our third root, 7.777777. 41 iterations. 41, that's not too good. We could do better with that, probably with other algorithms. But it's fast enough that we can stick with that, and we're happy. We found our third root. On to the fourth root. So we will do the same thing. Yeah, we'll zoom in. And we'll pick some numbers. What about, I don't know, 11.9 and 12? We'll pick two numbers here, and then the secant method can converge on it. So 11.9 and 12. We'll copy and paste that. 11.9 and 12. We'll keep the same tolerance. And there's our fourth root. Now, suppose I had asked for 9 digits of precision. All right, so worst case, we have 1 digit. We need 8 decimals here. So if we need 8 decimals, 1 times 10 to the minus 8, that would be the tolerance right at that 8th decimal. And we probably want it 2 orders of magnitude different to ensure that we have that kind of accuracy. So I'm going to go ahead and type in minus 10s for all of these. Remember, we're after 9 digits of precision, but we also need to update this. So this will be 10.8. And I'm going to copy and paste that all the way down so that we're displaying all of our 9 digits. And let's go ahead and run it. And notice the number of iterations didn't change too much. That first one did, which I think just indicates more that the secant method probably isn't the best method to find that first root. So that's really it. That's how root finding is done. And maybe it's a little bit more crude than you were expecting. And it takes some initial exploration, playing around with the axis limits to zoom in on the roots. But once we do that, we can make a pretty good educated guess of whether these are, single, double, triple, quadruple. We can zoom in, get our rough estimates of the root. We can then seed our root finding algorithms with those rough estimates, and they can refine those very quickly. Oh, I found one horrible mistake. Find root 4. Okay, that makes all the difference. All right, well, I hope you found this instructive and meaningful, and this will help you in your future root finding endeavors. See you.